Hi everyone, welcome to Chem 2. My name is Professor Verissimo and I will be your instructor this semester. So Chem 2 picks up exactly where Chem 1 left off. So we are going to start with chapter 14 in your textbook, which is the study of chemical kinetics, or how fast or slow a reaction will go. So first we're going to talk about ectotherms. And ectotherms are cold-blooded animals like lizards or other things like that, right? And these are animals whose body temperature matches whatever environment they're in. So if a lizard is sitting in the shade where it's cooler, they're going to have a cooler body temperature. And if they're out in the sun, then they're going to have a warmer body temperature, right? This is why you often see the lizards out, sitting on houses, right, to try and warm up. Because when a lizard's body temperature drops, all of the chemical reactions that are occurring in its body slow down. And this is true for all chemical reactions. Anytime we slow down we cool down a chemical reaction, we're causing the reaction rate to go slower. And so in a lizard, this causes it to become lethargic and slow down in other ways. So chemical kinetics is the study of factors that affect the rates of the reaction, right? Anything that's going to affect how fast or slow our reaction will go. One of these is temperature, but we are going to look at lots of different factors. So again, chemical kinetics, we're looking at the speed of the reaction, and we call this the reaction rate. And the rate of the reaction is just how fast our reaction is going to make products or how fast it's going to use up its reactants. And the ability to control the speed of this chemical reaction is really important because sometimes if the reaction goes too fast, it will make a product that we don't want, right? Chemical reactions don't always make this one product. Sometimes they can make other things. And so if by controlling the speed of our reaction, we can figure out which product we actually will get. Oftentimes, we also want our reactions to go faster just because we don't want to sit around all day and wait for them to happen. So the ability to control our speed, really important. All right, so first let's talk about rates in general. And rates is something that you are familiar with, right, from driving your car, right? We use our rate in our speed, miles per hour. So however far you can go in an hour, that would be your speed, your rate. So if we were going, 60 miles per hour on the freeway, that means in 1 hour, you will drive 60 miles if you set it on, cruise control. Anyway, so any rate is just how much of something is changing in a given period of time. So in this example, our distance is changing, right? How far we went in a given period of time. Most times in our chemical reactions, we're looking at how much the concentration is changing in a given period of time, either of the reactants or of the products. So the rate of a chemical reaction is generally measured in terms of the concentration of a reactant decreasing or how much the product will increase in a given period of time. Okay? When we're looking at the reaction rates, typically we will put a negative sign out in front of the reactants. And this is because the reactants are going to decrease in concentration over time, whereas the products will increase in concentration over time, right? We're going to use up our reactants to make our products. So our reactants will get a negative sign on their rate, and our products will get a positive sign. Here, hopefully we're all familiar with this, the triangle, the Greek letter delta, that means change. And so we're looking at our change, and the brackets here are always going to mean concentration. So this is often going to be molarity, right? This will be moles over liters, or, capital M. And so we're looking at how much our molarity is going to change per time. And this is typically in seconds, but not always. And so we're always going to do final minus initial. So our concentration at time 2, right, our final time minus our concentration at time 1, and then, our time 2 minus time 1. Okay, so this would be our rate, our change in our molarity per seconds. So this would be our unit for rate, molarity per second. You'll also sometimes see it written as molarity in s to the minus 1, or sometimes like this with a dot. Any of those is correct. They all mean the exact same thing. So if you're seeing those, they all mean the same thing. So So we have two different kinds of rates that we're going to talk about. We're going to talk about instantaneous rates and average rates. The instantaneous rate is the change in concentration at any one particular time. And typically our rate curves are going to be they kind of look like this. They're going to be curves, our changes in concentration. And so our instantaneous rate is going to be the slope at any one point in the curve. So say we were going to look at our instantaneous rate here. Well, we would look at the tangent line, right? And so some of you who have taken calculus are like, hey, this looks familiar, right? We're not actually going to use calculus in this class, don't worry. But the instantaneous rate is going to be determined by taking the slope of a line tangent to the curve at that particular point. You don't have to do any kind of derivatives. You'll be given all of the points, and you're just going to use that formula that we did before with our change in our concentration over our change in time. So here it is. So if we were looking at our instantaneous rate of hydrogen iodide, right? So that is a product. So as you can see, over time, our curve, is going up, right? We are increasing the amount that we have, and we are, decreasing our amount of hydrogen because our hydrogen is getting used up to make our product. And so if we were looking at, this time is, 50 seconds or so. If we're looking at our time here, we would take the slope of the line tangent at that point. So we would look at, our change in molarity over our change in time. So this would be, 0.56 molar over 40 seconds to get that instantaneous rate. And then we would look at, this over this to get that instantaneous rate. But it's the slope of the line tangent to the curve at that point. That would be for our instantaneous rate. But as you can see, right, if we look at this particular graph over time, our slope will change. Like up here, right, we have, our slope is not as steep anymore. It starts to flatten off. So our rates are not constant, okay? Our rates are constantly changing. As the time goes on, the rate of a reaction generally slows down because our concentration of the reactants decreases. If we think about our reactions in terms of collisions, okay, and we're going to talk about reactions in terms of collisions quite a bit. But if we think about collisions, we need our reactant molecules to crash into each other in order to make the reaction go. Well, if there's fewer of these reactant molecules, then the likelihood of them crashing into each other decreases. So our reaction rate decreases because our concentration is decreasing, right? Then not as many will be able to collide with each other as it was at the beginning when we had tons of them, right? Collisions all around. So over time, our reaction rate will slow down. And after a while, at some time, the reaction will either stop because we completely run out of reactants, or because the system has reached equilibrium, which means that the reactants are making the products, but then the products can re-react and make the reactants again. We are going to look at equilibrium in the next chapter. But for now, what I want you to know is that the reaction is generally going to slow down because the concentration of the reactants decreases. Okay. So our other type of rate that we were going to talk about was the average rate. The average rate is the change in measured concentrations over a given time period, right? Maybe say over 40 seconds or so. And this is going to make a linear approximation of a curve. So again, if our curve looked like this, right, we're going to say, okay, well, instead of taking, the slope of the line tangent, that would be our instantaneous rate, we're just going to say, instead of this being a curve, we're just going to pretend it's a straight line, right? So this does not tell you as much information about your rate because it's missing all of this instantaneous rate that's happening in the middle. We're just taking an average rate, okay? It's instead of making it being a line, we're going to take a linear approximation. And the larger the time interval, right, the larger, like here, I took from, let's say like this time to this time or whatever the case may be. But the larger the time interval, the more that average rate is going to deviate from the instantaneous rate. Because here, like, let's look at this instantaneous rate. Well, that looks like that, right? It's a fairly straight line. Well, that's very different than this average rate that we have going on here. Okay, so the larger you make this time interval, the more your average rate is going to differ from your instantaneous rate. So here we have a bunch of instantaneous rates down here. And if you look, right, they're very different. At the beginning, our instantaneous rate is very fast. And toward the end, as we start to run out of our reactants, it ends up being much slower. So if we were going to take an average of these, right, maybe it falls, somewhere in the middle, then like that doesn't tell us as much about our reaction in general, okay? So getting these instantaneous rates, much more informative than our average rate. So we can use stoichiometry to look at our reaction rates, right? Because most times it's not this one thing plus this one thing makes this one thing, right? We usually have coefficients, right? They don't all normally react on a 1-to-1 ratio. That's not very common. And so for the reaction that's written here, for every 1 mole of hydrogen that's reacting, we will also use up 1 mole of iodine, and we will produce 2 moles of hydrogen iodide, okay? The reaction rate will be, or the rate of change will be different for all of these because, these will be decreasing as a factor of 1, whereas it will be produced at double the rate, okay? The way that we write this out is we are always going to have it be 1 over our coefficient, okay? So that's what these A, B, C, D's down here, these are our coefficients. So this is assuming that we had A plus B gives C plus D, okay? So that's why they have negatives here. Our negatives are showing that these are reactants, right? They're being used up, and we have positives over here showing that these are products and they're being used. So these coefficients here is like if this was out front, right? And so we're always going to have 1 over our coefficient to look at our rate of change, okay? And this will be how we can calculate the reaction rate of the overall reaction. So this will make more sense in an example. So let's go ahead and flip forward. So if we look at the concentration of hydrogen, okay, the instantaneous rate at 50 seconds, this is the same we were looking at earlier, right? At 50 seconds, we are losing, right, negative 0.28 molar, and that is in a 40-second time span that we're looking at, okay? We could have, just to note, we could have stretched this all the way out here, which is what it's going to do on Alex, and it will use these, the points on the axes, okay? Instead of using these random points that it has on this diagram, Alex will use this point and this point when we are doing instantaneous rate, just a heads up. Okay, but we're looking at just this section of our tangent line, okay? And so for every, 0.28 molar is 40 seconds. So our rate is 0.0070 molar per second, right? And again, you can write this as molarity, s to the -1. Sometimes you can write it like this, right? If we were looking at hydrogen iodide, we would do the instantaneous rate at 50 seconds. We do it the same way, right? We do 0.56 molar over 40 seconds, but here we have a coefficient now on our hydrogen iodide. So we're going to use 1/2, okay? Because remember, it's always going to be 1 over the coefficient, okay? So if you'll look, when we do that, that gets us the same rate of the reaction. Okay, so no matter which thing we use, we will always be able to calculate the rate of the reaction if we, and it will always be the same as long as we incorporate these coefficients, okay, the numbers in the front. Here you'll notice, okay, we have a negative here and a negative here. Okay, so this negative is because our products our reactants are disappearing, right? We're always going to put a negative in front of our reactants. This here is because when we did final minus initial, right, our final is down here and our initial is up here, and that's getting us a negative number, okay? So this will always come out positive. Your rates will always come out positive. We write them positive by convention. So that's why we have this, the double negative, so it ends up being positive. Okay, summary of what we've talked about today. So here we have our reaction, and we, when we look at this, we have our nitrogen dioxide is producing nitrogen monoxide and oxygen gas. Okay, so if we look, the green line that represents nitrogen dioxide is decreasing over time because it is a reactant. Nitrogen monoxide and oxygen gas are both increasing over time because they are products. So we can measure the disappearance of the reactants. We can also measure the appearance of the products. And remember, it doesn't matter which one of these we use to measure the rate, as long as we are incorporating the coefficients, right, the 1 over the coefficient, we can always calculate our rates. Okay, and they are proportional stoichiometrically, which means, right, that those coefficients are coming into play. For every 1 oxygen, right, there's a imaginary 1 here, for every 1 O2 that's being produced, we are producing 2 nitrogen monoxides. Okay, these are proportional stoichiometrically. The instantaneous rate is equal to the slope tangent to that point. So if this was our point, right, we can, our instantaneous rate is going to be equal to the slope that's tangent at that point. And we're always going to do the change in our concentration. So here we have our change in nitrogen dioxide over our change in time. And remember, that will always get us a positive number, because even though we're doing final minus initial, right, which would come out negative because it's decreasing, we're putting a negative out front so that that whole thing becomes positive. And then over time, our reaction rate is changing as the reaction proceeds, because, right, that rate, right, we're looking at how fast things can bump into each other, or how frequently things can bump into each other. If we have fewer reactants, right, if we have a lower concentration of our reactants, then them bumping into each other is not as common, so our reaction rate will decrease. This last bit says, if the rate is dependent upon concentration. That's a spoiler alert. We're going to look a little bit later about things that are called zero-order reactions, in which the rate it can be independent of concentration. But in general, the rate will change as the concentration changes, right? So as the reaction proceeds, the rate will change. Again, not for zero order, but more on that a little later. So the change in the rate, right, our change in our concentration over our change in time, which is our rate, is not a constant, okay? Our slope is continually changing, okay? And that's it for today. This was our introduction to chemical kinetics, our introduction to rates. Next time, we are going to start looking at how to determine the rate of a reaction once we're given a chemical equation. So I want to tell you now, if you haven't taken a class from me before, I have posted these chapter lecture worksheets. So the lecture worksheet that goes with this one is the chapter 14 lecture worksheet. It's available on Canvas, and the answer key is also posted. These are not for points. They, do them or don't do them. Obviously, I recommend that you do them. I did them all, right? I did the answer key. The point of those lecture worksheets is so that you can get practice doing problems. The problems in ALEKS tend to be much more challenging than the problems in the lecture worksheet. I like to think of the lecture worksheet problems as kind of your introductory problems, and they build up to the ALEKS problems. The lecture worksheets are not for points. They will never be collected. I will never ask whether or not you've done them. But remember, I write the lecture worksheets. I also write the tests and the quizzes and the final, right? So if I'm writing these types of problems and I'm giving them to you to help you, you may want to do them to see what kinds of problems are likely to be on the tests and quizzes. So again, it's to help you practice. It's to help you get ready for the tests and quizzes. It's to help you do the ALEKS assignment. I would always, just in general, watch the lectures. Let's start over. I would always read the chapter, then I would watch the lectures, then do the lecture worksheet problems that I have assigned for that lecture, and then go and do the ALEKS assignments. People like to just try and skip to the ALEKS assignments, and sometimes they'll get really frustrated because they don't understand how to do the problems. Well, likely that's because you haven't gone through and done the lecture worksheet problems to practice those types of problems. So if you find yourself getting frustrated with Alex, the first thing I'm always going to ask you is, did you do the lecture worksheet problems? So that's it for today. This was our introduction to chapter 14. If you have any questions, please send me a message on Remind. I use Remind really frequently to send you messages and to communicate with you. So if you have a question, just send me a text message on Remind. It only goes to me. It doesn't go to the rest of the class. My initial messages go to everyone, and then if you message me, then we just have a conversation back and forth, and no one else will see it. So if you have a question, please feel free to send it my way. You can also send me questions via email. You can write your questions on the discussion boards. You can attend my office hours and ask me there. There are lots of ways to get help. If you find yourself struggling at any point in the course, please, please, please reach out. Remember that I became a chemistry instructor because I like to talk about chemistry and I like to help students. So if you ever need any help, please send your questions my way and I will be happy to help you. All right, I'll let you guys go now. Get some work on chapter 14. Welcome to Chem 2. I'm excited to have you here and I will talk to you all next time.